seja mais um inscrito no canal. E não se esqueça de deixar o seu curtir like no vídeo.
Easter Island. Here, the world's leading solar astronomers race to witness one of nature's great natural wonders, a total eclipse of the sun.
To get a complete picture of the sun, we have to go to eclipses.
Their goal, discover new clues to the sun's deepest mysteries and unlock secrets of the universe.
I don't think everybody understands how complicated the physics behind this type of object really is.
Throughout history, eclipses have brought warring nations to their knees.
They thought it was an act of the gods and that it might be the end of the world.
Provided key evidence in the search for the world's future energy needs.
It'll be a game changer.
Even affirmed Einstein's theory of relativity. Seen as never before in a place of archaeological wonder, the Easter Island eclipse. Easter Island, one of the most famous yet remote archaeological sites in the world. To these isolated and mysterious shores, leading solar scientists have come to observe and analyze one of astronomy's most spectacular events, a total solar eclipse.
Easter Island, what a great location for an eclipse.
Located 3,200 kilometers off the South American coast of Chile, the island's 165 square kilometer landscape is rugged and remote, formed from the remains of 3 extinct undersea volcanoes. Months of preparation have gone into these expeditions.
This looks very interesting.
And astronomers must choose their observation sites carefully. The Easter Island eclipse will last for less than 5 minutes. A narrow window of time for scientists to complete their detailed work, made even narrower by the threat of bad weather.
Okay, this is it. I think we finally found the place.
All right.
If all goes well, eclipse scientists will observe key regions of the sun that are best seen from Earth during a total eclipse. Not only do those regions hold essential secrets to the sun's inner workings, they have a direct impact on life here on Earth. Throughout time, the sun has been the one constant in our otherwise unpredictable history. It rises and sets, the giver of all life. Yet the sun is also a star, one of an estimated 200 billion in the Milky Way galaxy. And even though solar satellites now provide varied and detailed views, the sun remains ruled by laws of physics and unimaginable forces that we are only beginning to grasp.
When you look in detail at the sun, you can see that it's filled with very dynamic and very large events. And understanding these things and how those changes affect us here on the Earth is something that we're still barely being able to do.
And as scientists now recognize, even though the sun is 150 million kilometers away, this solar activity can pose a very real threat to our way of life. March 13th, 1989. Quebec, Canada's hydroelectric power system collapses in less than 90 seconds. Voltage swings wildly across the North American power grid. A nuclear power plant falters. The cause? A geomagnetic storm born on the surface of the sun.
What you've got going on in the core of the sun are millions and millions of hydrogen bombs going off per second, compressed and held in by the gravity of the sun.
October 2003, a series of solar blasts equal to many billion megatons of TNT send shockwaves of solar particles past the NASA solar satellite SOHO, headed toward Earth. When those particles hit, less than 1 day later, satellite communications were disrupted. Authorities ordered transcontinental airlines to reroute, while astronauts aboard the International Space Station took cover, their mission, and possibly their futures, at risk.
This storm came around and produced some of the most intense electromagnetic disturbances in the space environment of the Earth that we've seen for a really, really long time.
Because solar storms threaten so much of society's advanced technology, learning to predict their occurrence has become a priority for space agencies around the world. Astronomers now call this new field space weather.
Space weather is a field that didn't exist 15 years ago. And now it's spread across several government agencies, and we're getting funding to do the research to try to understand it and be able to predict it.
But not all of solar science can be conducted in space. Cost alone makes it prohibitive.
We've got some great spacecraft to study the sun. We've got some great mountaintop observatories to study the sun. But there are still many things that we learn at eclipses that we can't learn at other times. To get a complete picture of the sun, we have to go to eclipses.
Approximately every 18 months, a total solar eclipse occurs somewhere in the world. Its timing and location dependent on the movement and rotations of the sun, earth, and moon.
A solar eclipse occurs when the moon happens to get in the right spot between the sun and the earth, casting a shadow on the earth. So the earth is basically moving through the moon's shadow, and that's what a solar eclipse is.
Predicting when and where an eclipse will occur reflects our basic understanding of planetary motion. Every 29.5 days, the moon completes a single orbit around the Earth. That means that once a month, the moon passes in between the Earth and the sun, raising the possibility that a solar eclipse might occur. But it's no sure thing. Why? Because the moon's orbit is actually tilted 5 degrees relative to the Earth's. So as the moon and Earth orbit the sun, the relative position where the moon crosses between Earth and sun changes. In most months, the moon is simply too high or too low to cast a shadow on Earth's surface. That shadow simply goes off into space, and no eclipse occurs. When a solar eclipse does occur, most of the time the moon only covers a portion of the sun, while at others, it becomes engulfed in a ring of fire. But approximately 25% of the time, the sun, moon, and Earth glide into so exact an alignment that the sun's surface is totally obscured, a total eclipse of the sun. That it occurs at all is a stunning coincidence of celestial geometry. Measuring 1.4 million kilometers at its diameter, the sun is approximately 400 times larger than our moon. But the moon is 400 times closer to Earth. What this size-to-distance ratio means is that to us, on Earth, both the sun and moon appear virtually the same size in the sky.
This ratio of 400 times larger to the 400 times closer creates a perfect situation where the moon completely blocks out the solar surface and allows us on Earth to see a total solar eclipse. And it's just a really neat coincidence that this distance and size ratio exists.
Never lasting more than 8 minutes, the period when the sun, moon, and Earth come into perfect alignment is called totality. And with its bright glare removed, the sun's hidden secrets are suddenly exposed.
The sun's a great big ball of gas, a million miles across, and we see that hot everyday surface giving us a lot of light. But that's just a fuzzy atmosphere. It just happens to look sharp because we can't see the edge in such detail. But there's a whole region just around the everyday sun that we can see best at eclipses.
Scientists refer to the bright everyday surface of the sun as the photosphere. When the photosphere's light is covered during a total solar eclipse, what appear are 2 otherwise invisible regions of the sun: the chromosphere, the thin red layer along the solar edge, and the corona, the sun's outer atmosphere. Not only do these regions reveal much about the everyday workings of the sun, but it is within them that violent solar storms rise and erupt. So being able to see and study these regions, however briefly, is why scientists go to eclipses. But why Easter Island? Shouldn't everyone be able to see the total eclipse from their own backyard?
Well, it seems natural that during the time of the eclipse, anyone standing on a side of the Earth facing the sun should be able to see the eclipse. But that's not how it works. There are actually two shadows that the moon casts upon the Earth. This first one, it's very large and very diffuse, thousands of miles in size, is the penumbral shadow. Inside of the penumbral shadow, an observer can only expect to see a partial eclipse of the sun. The moon doesn't completely block out the sun. But here, in this much smaller, much darker shadow, the umbral shadow, no more than a couple of 100 miles in size, the moon completely blocks out the sun, and here you can expect to see a total eclipse.
The trajectory of that umbra shadow across the face of the Earth is known as the path of totality. For the Easter Island eclipse, that path will begin just south of the South Pacific Isle of Tonga, then race easterly at more than 1,600 kilometers per hour.
The length of that path might be 10 or 12,000 miles long, but it's very narrow and it only covers a small fraction of 1% of the Earth's surface.
So when we're preparing to observe an eclipse, we look on a map and we see where that path is going to cover, where we have to be within the path. It turns out that the only substantial land it goes over is Easter Island. And other than that, it's going over Pacific Ocean.
Today, knowing when and where a total eclipse will occur can be predicted down to the second. Yet that doesn't make the job of our Easter Island eclipse scientists any less difficult.
We're going to be ready, but we are going to need the equipment all functioning. We are going to need good weather. If something goes wrong, then it's more than a couple of years until the next total solar eclipse.
Will the weather cooperate? And what clues to the sun's mysteries will scientists discover in the hours to come? Only time will tell as the countdown to the Easter Island eclipse begins. The sun. Never before have we better understood its massive scale, nor devoted so much attention to its most explosive features.
The energy output of the sun is hard to imagine, but if we stop for a second and consider the amount of energy that man has produced over the past 5 or 10,000 years, the sun produces 1,000,000 times more energy every second.
The sun's violent storms rise within the solar atmosphere, including the corona, the region of the sun that can best be observed from Earth during a total solar eclipse. With the stakes high, scientists have raced to the Easter Island eclipse. If all goes well, they'll make detailed observations of the corona in order to begin to master its secrets. Their investigation begins with current theories that the corona generates a steady stream of solar particles that blow outward into space, the solar wind.
That corona doesn't just stop at some hard boundary, it actually streams outward. The entire solar system is permeated by this ever outflowing, constantly dynamically changing wind.
And this wind blows past all the planets, the asteroids, all the way to the very edge of the solar system.
How the sun's corona accelerates that wind is a crucial question for eclipse scientists, especially those focused on its violent storms. Yet the sun's corona is so complex that even its basic features seem to defy everyday physics here on Earth. Beginning with an illogical puzzle. Why is the corona so hot?
If you're sitting in front of a stove and you're too hot, you move away and it gets cooler. Well, if you're at the solar photosphere, the everyday surface of the sun, and you move away, you move outward into the chromosphere of corona, it gets hotter. So that seems odd offhand, and so why is that?
Temperatures inside the solar core boil at 15 million degrees Celsius, but cool to 5,500 degrees Celsius by the time they reach the sun's surface. Yet continue outward into the corona, and temperatures suddenly soar back up, ranging from 550,000 to 2.7 million degrees Celsius.
It's doing something that we don't quite understand. It's transporting energy from the cold part to the hot part.
In fact, the distance from which it goes from about 10,000 degrees to this million degree is only on the order of like 50 miles.
During the Easter Island eclipse, scientists will use their brief access to the corona to find answers to this strange contradiction.
The problem has been solved. It's been solved a dozen times over, and there are a dozen different answers. So, of course, that means it really hasn't been solved, and we want to choose among those different solutions.
On Easter Island, many scientists will focus their attention on a very narrow portion of the sun, the inner corona, where the corona and photosphere interface, a region that appears no larger than a human hair to the naked eye. To make their observations, scientists must deploy a variety of powerful optical devices to gather and record their data.
We have studied the inner solar corona using the large spectrograph, which is possible only during the total solar eclipses.
In this regard, modern eclipse science hasn't changed all that much since its inception during the 19th century. Modern eclipse science began in the 1840s, when a new wave of European scientists made crucial observations of the sun and corona that laid the cornerstones for today's solar studies.
There was a total eclipse that passed through Europe in 1842, and that was the first time in centuries that any European scientist had a chance to see a total eclipse. They were totally amazed at the corona. They didn't know anything about the corona, so here was a new mystery to try to uncover.
19th century eclipse scientists were among the first to use photography, which had been invented only years before. And they would soon employ another new invention, a spectroscope.
Spectroscopy allows us to take light from a faraway source and compare it to standards here on Earth to figure out what something's made out of.
Heat any chemical element from the periodic chart, like potassium, and it will reveal a distinct color. When viewed through a spectroscope, that color forms a very specific pattern of bright lines across the spectrum, like a fingerprint, unique only to that element. Compare potassium's spectral pattern to lithium, then to iron.
If we know that sodium burns with a certain color, and we see that same color coming from a foreign object, in this case the sun, we can be positive that that sodium is present there. We can even infer by their intensities how much of those elements are present.
Spectroscopy initiated a rapid new understanding of the sun, including the recognition that it was made of hydrogen in the form of superhot gas, today known as plasma. Next, eclipse scientists armed with spectroscopes discovered the element helium, never before seen, but now accepted as the second most abundant element in the universe.
This new element that was discovered was given the name helium for the sun, Helios.
The discovery of helium by eclipse scientists marked a turning point in our understanding of the sun. The first hint of the complex thermonuclear engine churning within its core, an engine fueled by nuclear fusion.
Fusion is a nuclear reaction which produces energy. It's when light atomic nuclei, usually isotopes of hydrogen, combine to form heavier atomic nuclei, and energy is released in the process.
At normal temperatures, hydrogen atoms repel one another, just like two common magnets. But within the intense heat of the solar core, that repulsion is overcome. Hydrogen nuclei now collide, fusing together to form helium and releasing intense energy in the form of gamma rays. Even at the speed of light, their journey will last up to 1 million years as they randomly bump their way through the dense mass of particles. Those rays finally emerge from the surface of the sun as light for their 8-minute trip to Earth. So next time you go outside on a sunny day, remember, that light was generated within the sun's core up to 1 million years ago. Here at the Massachusetts Institute of Technology's Plasma Fusion Center, researchers believe that fusion may one day solve the world's energy needs, beginning with experiments inside a fusion reactor, known as the Alcator CMOD, one of only 3 in the country.
3, 2, 1. Entering pulse.
Well, it only lasts 2 seconds, but during those 2 seconds, we're pumping the power demand of an entire city into a small chamber a few meters in diameter. It's really an amazing thing that happens here every 20 minutes.
For now, the physics of plasma and nuclear fusion are so complex that any chance of recreating the sun's nuclear furnace remains only an exciting experiment. But hope remains high.
We really believe that we can have a major impact on the future energy balance of the world. And if we are successful, it'll be a game changer.
In just a few minutes, the Easter Island eclipse will begin with what scientists term first contact, the instant when the moon begins to cover the sun. It is the first stage on the march to totality. Yet for most viewers here on Easter Island, first contact will be invisible. When viewed only with the naked eye, the strong glare of the sun remains too blindingly bright. To overcome this glare, Eclipse scientists deploy a variety of solar filters on their telescopes and other instruments. Few more powerful than those on this new mobile solar telescope, which filters the sun's light at the wavelength hydrogen alpha.
There's been very little information done about what you can actually see through a hydrogen alpha filter during an eclipse. So yeah, we get to see probably some very exciting phenomenon occurring once that starts to happen.
One of the most exciting and important phenomena that scientists hope to see during the Easter Island eclipse are solar prominences. Fiery red arcs of plasma that twist outward from the sun's surface. This is space weather in action, captured here in time-lapse photography. And only during a total solar eclipse are these prominences visible to the naked eye.
These are bright red clouds of hydrogen gas aimed close to the surface of the sun, and they extend out beyond the edge of the moon as these red tongues of fire.
Although prominences appear small during an eclipse, as much as 100 billion tons of solar plasma flow through these majestic loops that can rise over 160,000 kilometers into space, to a height over 12 times the diameter of Earth. Often, these prominences can turn inexplicably violent, hurling the equivalent energy of millions of hydrogen bombs into space. To understand the forces that generate these prominences from within the sun, scientists use not only sight, but sound. What you hear is the vibrating heartbeat of the sun, enhanced by audio engineering. Through a remarkable science known as helioseismology, scientists can use the sun's acoustic waves to create a virtual ultrasound of the sun's interior, just as earthbound geologists use sound to probe for oil or potential earthquake fault lines. What that ultrasound reveals is a sun in constant twisting motion.
The sun is a huge ball of very, very hot gas, and it's not solid like the Earth, and so it will actually rotate at different speeds depending on where it is on the surface and inside the sun.
Deep inside the sun, solar plasma completes one full rotation approximately every 27 days, a speed slightly slower than on the surface at the equator. At mid-latitude, the sun's rotation takes nearly 26 days, and at the poles, nearly 34 days.
So it's all this gas that's basically rotating at different speeds. And I don't think everybody understands how complicated the physics behind this type of object really is.
Scientists theorize that as these huge walls of plasma spin and shear against one another, they function like a giant power station, creating powerful electric currents and intense magnetism. The sun's magnetic dynamo.
A dynamo means some mechanism for converting mechanical motion into electricity. So it is believed that there's something moving around in the sun, and that's making electricity in effect, and that electricity is making magnetic fields.
And it is those magnetic fields that form solar prominences, creating the loop-like structures that scientists often observe during a total eclipse.
A magnetized plasma has a very organized, magnetically organized way of behaving. That's why when you look on the surface of the sun at these beautiful NASA images, you'll see these archways of plasma. What's happening is you've got a magnetic loop that is bubbling through the surface of the sun. Then the plasma that makes up the sun has an easy time filling up this loop, but then it's trapped. It's magnetically confined, as we say.
The large magnetic loops of plasma that form prominences rise upward from the sun's surface and into the corona, yet are held by other magnetic fields, creating an ever-building pressure.
One way to picture it is that the magnetic field lines are kind of like rubber bands, and you stretch them only so long and then they snap. But when they snap, they instantly reconnect into another reconfiguration.
No one fully understands what triggers these prominences to snap, but the result is clear. An eruption of solar plasma traveling millions of kilometers an hour into the solar system. These explosions are called coronal mass ejections. When this explosive wave of solar particles hits Earth, our own magnetosphere blunts much of its impact, forming stunning light displays known as auroras. But the bigger the solar storm, the greater the potential havoc.
A solar storm can actually produce catastrophic effect on this planet, which can be about 20 times more economic damage than the Hurricane Katrina produced.
"384,000 kilometers above the Earth, the Moon has now moved into the first stages of alignment with the Sun. In less than 90 minutes, totality will begin." After so much work, only the weather can interfere with the crucial views that scientists have traveled so far to see. The Easter Island eclipse is less than 15 minutes away. With the clock ticking, eclipse scientists scan the sky for changes in the weather.
7 minutes to go. Couldn't be better. Look at that. Sky clear from there to there.
The Easter Island eclipse could prove significant not just in the race to understand space weather, but also to answer some potentially troubling questions about the sun's long-term future. And ours. As dynamic and volatile as the sun can be, it also displays measurable consistencies, including an 11-year rise, fall, and rise in its magnetic activity, known as the solar cycle. Every 11 years, the sun's behavior changes from relative calm, known as solar minimum, to a period of frenetic and stormy magnetic activity, solar maximum, and then back again.
That's kind of the way nature works in cycles. It goes from maximum to minimum. It's pretty regular, but there are times when it does things we don't expect.
And when that solar cycle varies from its predicted course, as it's doing right now, Eclipse scientists have reason to worry.
Earth is on a very delicate balance with the energy budget that we receive from the sun. Any small fluctuations will have important ramifications for life here on Earth. In one case, it could produce ice ages. In another case, it could produce drought and even evaporate the seas.
A massive increase in the sun's magnetic activity during an intense solar maximum could, some scientists theorize, lead to temperature increases within the Earth's oceans and changes in the winds, rains, and winter storms. But that's not the concern right now. In fact, just the opposite is true. For more than 3 years, we've been in a prolonged solar minimum, creating striking changes in the sun's behavior.
So the whole sun is very quiet, the corona is very quiet, it's melting away to some extent. We've seen the extent of the corona diminish from the 2006 eclipse we observed in Greece to the 2008 eclipse we observed in Siberia to the 2009 eclipse we observed in China, and probably it will be even more diminished in the 2010 eclipse on Easter Island. We haven't seen anything like this in at least 100 years.
Could this extended period of solar minimum portend colder times ahead? No one knows for sure. But recent research using Arctic ice core samples matched to historic records seems to suggest that the last great fall-off in solar activity, known as the Maunder minimum, resulted in intensified winters during the 17th and 18th centuries. Some call this past era, when overall temperatures dropped by as much as 1.5 degrees Celsius, the Little Ice Age.
So it's getting to a very interesting, maybe even worrisome situation.
At some point, if the sun really changes its activity level, we're talking about survival of our species at the level we would like to maintain.
One approach to monitor these solar fluctuations is to maintain a constant vigil of the sun's diameter. Variations in the Earth's atmosphere, coupled with the sun's distorting glare, make measuring the sun's diameter near impossible on an ordinary day. Not so during a total solar eclipse, when the size of the moon's shadow provides the essential clue. Positioning themselves at the outer limits of the path of totality, two teams of observers, one at the north side and the other at the south, can mark the edges of the moon's umbra shadow to within 100 meters. Once the umbra's overall size is determined, scientists simply work backwards, using the known size of the moon and the known distances to the moon and sun to calculate the sun's size to within a mere 32 kilometers.
And then you can compare that to eclipses taking place in other years in the past and see if the sun's diameter has changed between these different eclipses.
Careful calculations have always been central to eclipse science, and some of those calculations have changed the very way we view our universe.
When Einstein came up with his theory of relativity, he realized that one way to test it was during an eclipse.
Does gravity affect light, even bend it like a lens? It seems hard to believe, but Einstein's theory said yes. But only an object as large as the sun could generate enough gravity to allow us to see those changes. So in 1919, eclipse scientists set out to prove him right. The concept was simple. Photograph a group of stars when they're observed unobstructed by an eclipse. Then photograph them again during a total solar eclipse when nearly hidden by the eclipse. If Einstein's theory were correct, the stars would appear slightly offset to the viewer on Earth because the sun's gravity would bend their light, causing the observed location of the stars to shift.
And Einstein's theory predicted how much those stars should shift in a photographic plate, and it turns out he was exactly correct.
Today, relativity impacts not just our understanding of astronomical wonders like black holes, but how NASA lands a rover on Mars, as well as guaranteeing the GPS navigation system in your car.
From an everyday standpoint, things like GPS absolutely would not work if you did not include the effects of relativity. The whole GPS system would be worthless if you didn't have relativity.
So the next time you take a cross-country trip, remember that a total solar eclipse helped get you where you wanted to go. In just a few minutes, the Easter Island eclipse will begin. Just hours ago, the moon's umbral shadow first fell across the Earth, deep in the South Seas, and began to race along the path of totality toward Easter Island at more than 1,600 kilometers per hour. Anticipation is high, and as veteran scientists make their final adjustments, they begin to watch for the breathtaking phenomena usually seen at the onset of a total solar eclipse.
It's a shock even to people in the 21st century. I've seen an eclipse, I knew exactly what was going to happen, when it was going to happen, down to the second, and I was still blown away when it actually happened.
The lighting during an eclipse is different than any other natural circumstance or unnatural circumstance. The horizon looks like dawn or dusk, but 360 degrees around.
I've seen cows heading back to the barn as though it were evening. Flowers begin to close up as though it were night. Sometimes bats might start coming out the last few minutes before totality.
Even the ground will start to dance and shimmer in unusual ways.
One of the most interesting effects that happens during the partial phases of a total eclipse, that is, things which are very ordinary, like a shadow from this plant, start to become very extraordinary. So what I've done is I've set up a 5,000 watt light to act as my sun, and I've created a disk which will act as my moon. So right now the sun is doing what it normally does. The light is shining onto this plant, and we see very ordinary shadows as we would normally expect. As the eclipse starts to happen, things change. And now I can see little eclipse suns on the ground. This is because light coming from my sun is trying to make its way through the plant. The leaves are blocking most of it, but the patterns of the leaves in the plant start to form tiny little spaces, pinholes. Due to the physics of the way light works, these little pinholes will focus the light and make actual focused images of the sun. And I can exaggerate that using my hand, and the spaces between my fingers will act as their own pinhole cameras, as if there are more leaves and a small breeze blowing, and those images will start to dance around on the ground, and it becomes a very incredible effect.
Surrounded by these eerie sensations, there are many who seek purification or shelter during an eclipse, based on traditions that date back centuries.
It really is very awe-inspiring to see it get dark in the middle of the day. The partial part of the eclipse takes an hour and a half or so. It gets gradually darker, but the last 15 minutes or so, you really see the light is strange, the shadows get very eerily sharp, and then the last 15 seconds or so, it gets about 1,000,000 times darker. When you look up, you see this diamond ring in the sky, a bright bead of sunlight.
As the moon covers the last remnant of the sun's bright glare, a final flash of light will appear in what is known as the diamond ring effect.
All of a sudden it gets 1,000,000 times brighter. To see it get 1,000,000 times darker and then 1,000,000 times brighter within a few seconds is just a fabulous thing.
Now this diamond is going to break up in a few seconds into a series of beads as sunlight shines down the narrow valleys along the moon's edge.
Those beads are caused by the last vestiges of sunlight shining through the mountains and crevices along the moon's edge, creating a sparkling effect known as Bailey's beads, named for the forefather of eclipse science. When these beads disappear, totality begins.
It'll look reddish around the edge of the sun. That'll be the chromosphere, a thin layer of the outer solar atmosphere. Then that'll get covered after a few seconds, and you see the corona for the duration of the eclipse.
Never does totality last more than 8 minutes. On Easter Island, it will last for 4 minutes and 41 seconds.
You can do a lot in 4 minutes. You can take a lot of photographs, you can take a lot of looks, and then all too soon you get these phenomena in reverse. The partial eclipse will still last another hour and a half, but it's been said that nobody ever saw the end of this partial eclipse because you're so excited.
So now we are ready. The cameras are locked. Researchers in position. We are only seconds from totality and the onset of the Easter Island eclipse. No longer do you have to imagine what the real Easter Island eclipse will be. Now, you are there. Easter Island. Scientists from around the world have gathered here to witness a total solar eclipse. The countdown has begun. In a matter of seconds, totality. There, a last burst of sunlight and a final halo, the diamond ring effect. The red edge you see is the first appearance of the chromosphere. We now stand in the full shadow of the moon. This is totality. The white wisps of the corona are now visible. Within its layers is born the solar wind, fueled as we watch by enigmatic forces that we have only begun to understand.
You can see streamers coming out with your naked eye.
Less than 4 days from now, particles within that wind will blow across Earth, bathing our North Pole and creating the aurora borealis. In 2 weeks, that same gust of solar wind will sweep over the moons of Jupiter.
This is the most incredible thing I've ever seen. It's nothing like the pictures. And you can, there's so many things you don't even realize.
Only beyond the orbit of Pluto, at the edges of the heliosphere, will this wind finally dissipate.
Everything's working. Everything's going so far. Yeah.
We are now nearly 4 minutes into the Easter Island eclipse.
Diamond ring.
The final stretch for eclipse scientists to make their last observations. In just a few more seconds, the sun's harsh glare will re-emerge along the western rim of the moon. And now, totality is over.
Oh, that's just fabulous.
Will the Easter Island eclipse prove decisive in the search for solutions to the sun's mysteries? There's no way to tell, at least not yet.
We then take the data back to Williams College and work on our computers for months or years to straighten things out.
What is clear is that solar science is never a sprint, only a marathon. It took almost 6 months to confirm Einstein's theory of relativity based on data from the 1919 eclipse. Easter Island will prove no different. Yet amidst such painstaking work, our sun, 93 million miles away, remains our nearest celestial laboratory.
If we can study one star in really great detail and learn what makes it tick, then we have the key to understanding essentially the rest of the universe. So we can look at stars that are really far away and they're a pinpoint of light, and okay, you can get a lot of information. Astronomers have done an amazing job, but there's really no substitute for being able to look up close at this amazing star.
In the meantime, across the world, the march to master the sun and predict space weather continues. With missions like the Solar Dynamic Observatory launched by NASA in 2010. And by 2018, Solar Probe, a mission that will fly directly into the teeth of the corona itself, locking into orbit 7 times closer to the sun than ever before.
You really need to probe out there that can actually touch, smell, taste the sun. That's what these sensors on Solar Probe will do. They will actually measure the particles, their velocity, their density, their magnetic field. I mean, how exciting is that?
But even as new technologies emerge in the race to solve the sun's greatest riddles, the experience of a total solar eclipse will never be obsolete. Not just for the rich history and traditions it represents, but as a constant reminder of nature's wonder and our eternal search to find our place within it.
Muito obrigado pela inscrição no canal e pelo seu curte e like.